physically possible. Yeah, you find the velocity gradient it's like 1/2 gradient plus gradient. I told you, but we just did this one.
So after, so try to grab your assignments, and after that, so this is both assignment 4 and assignment 5, and also other assignments that you might have given me back because there was some calculations. So take after you grab them, just give me the rest so that I take them to the geotechnical. Okay, so today is going to be a simple a lecture, concepts that you already know. We're not going to discuss any new concepts. We're just going to look at the beams from the perspective of continuum mechanics. So, as a structural engineer, you utilize the beam approximation in almost in 99% of what you do in the industry. 99% you look at structures, you look at columns and you look at beams, you analyze these, and you find what you call bending moments, shearing force, bending moments, shearing forces. Based on the bending moments and the shearing forces and the normal force, you design the structure according to what that structure can withstand in terms of the maximum moment, maximum shear force, maximum normal force. In doing so, you are already incorporating some or most of what we studied in continuum mechanics, but with a certain approximation. What we studied in continuum mechanics was based on continuum, an object that has 3 dimensions. Now, if that object has 1 dimension that's really long, then we're able, with some approximations, to consider this as a beam and apply everything that we studied to it and make it a beam with certain assumptions. And then there are 3 major assumptions. There are 2 types of beams that we're going to cover today. The Euler-Bernoulli beam, which is the basic beam that you analyze in your 372, in your 661. And there are 3 major assumptions that allow us to call a structure a beam. And the 3 major assumptions are: 1, small deformations; small deformations allow me to, when I write the equilibrium equation, instead of saying partial sigma to 1 by partial small x, or partial sigma ji by partial x j, I can almost say it's equal to partial sigma ji by partial capital X g. That's the first thing. Because of small deformations, the change of the stress with respect to the small x is almost equal to the change of the stress with capital X. not happy with the marking? Is he very strict?
Use up a certain panel. Yeah.
The important thing is to know what you did wrong. The mark is not a, as long as you got over 50%. Just the important thing is, if you don't know why you lost mark, that's the problem. Okay, so the small deformations. The second, one of the other assumptions that we use when we perform a beam analysis is we usually assume that it's linear elastic and isotropic material. Now, of course, you can analyze beam that's not linear elastic isotropic under the same assumptions, but for what we are going to study here, we're going to assume that it's a linear elastic isotropic material. Now, the most important one that allows you to look at an object as a beam is plane sections remain. So plane sections perpendicular to what we call the neutral axis of the beam before deformation remain plane and perpendicular to neutral axis after deformation. This is the major assumption behind the beam. So what did we just say? For me to be able to analyze this structure, now in general, this structure can deform, for example, like this. In general, this structure can, there's nothing that prevents it from deforming like that. But if it deforms like this, I'm not able to call it a beam. I'm not able to do any beam analysis on it. The only way I can consider it a beam is if when it deforms, so this I cannot consider a beam, or I cannot consider beam analysis. I can only consider beam analysis if, as the object deforms, plane sections that are perpendicular to the axis of the beam after deformation stay plane and stay perpendicular to the axis. If this assumption is valid or practically valid for whatever practical application I'm using, then I can conduct the beam analysis and do what I call the bending moment and shearing force and do all this thing. Without this assumption, I cannot do any beam analysis. So let's see what all these things lead to. So this will be the final result, and we'll see at the end of the analysis. So while everything that we did before was in terms of stresses acting on a small cube, because now I would like to analyze a beam, I would like to, instead of looking at a whole beam as a three-dimensional object, I would like to look at it as a one-dimensional object, or as a line object. So this point on the beam corresponds to a whole plane. Because this point corresponds to a whole plane, I'm going to replace the stresses, which are sigma on 1, sigma on 2, and sigma on 3, I'm going to replace them There's no Muhammad Abdurrahman, is there? There is. No Jikat, right? So these are the extra. Yeah. Now you know who you should talk to. So, because I would like to replace, because this point corresponds to a whole cross section, I'm going to replace what I call sigma on 1, sigma on 2, and sigma on 3 with their integration. So if I integrate sigma on 1, I obtain what I call the normal force acting on this point, which is basically all the stresses acting on this point, summed over that cross section. Shear 1, 2. So n is defined that way, just because of convention. Shear 1, 2 is defined in this direction, but I have defined sigma on 2 when we defined it in this course. We defined it upwards, and that's why there's a negative sign, just to reconcile the convention between how the shear is defined in textbooks or in the classical theory of beams, and how sigma on 2 is defined classically. So there's a negative sign to reconcile the difference. V13 is also negative. V13 is this way, it's also negative sigma on 3. M3, the moment, is the moment around the neutral axis of the beam. M3 is equal to the integral of negative x2 multiplied by sigma on 1, assuming that x2, that this neutral axis is x2 equals 0. And this is x2. So the moment around this axis is equal to the integral of negative x2 sigma on 1. Again, the negative sign is to reconcile what is positive, what is assumed positive in the classical beam theory, and what's assumed positive for sigma on 1. Sigma on 1 is assumed positive in this direction, but M3 is assumed positive in this direction. To reconcile those two different definitions or sign conventions, we add here negative. And so on for M2 and for L. The torque. Now we're going to be concerned with only two-dimensional beams. Two-dimensional beams were under bending, so we're only going to be concerned with M3 and V12, which we're going to call V. And this is what we're going to study for the Euler-Bernoulli beam. Okay. So exactly what we did for the regular, for the continuum, we extracted. For the continuum, we extracted the small cube. But for the beam, we're going to extract the whole sliver, because the point on a beam represents a whole cross section. So I'm going to extract a small sliver from the beam. The small sliver looks like this, and the definitions of the shear and the moment, I assume that the moment and the shear is a continuous function, similar to the stresses. They're continuous over my whole domain. I'm going to assume that their integration is also continuous on the whole domain, because their integration is continuous. Because their distribution is continuous along the whole domain, I can assume that if this is m, then right here I have m plus a little bit more. This little bit more is how m changes with respect to x1 multiplied by delta x1, plus a little bit more that I can ignore. And the same, if the shear, the value of the shear here is equal to V, then the shear on the other side of that sliver is equal to the shear plus a little bit more, and this little bit more can be approximated using a Taylor series. And similarly for the normal force, but we're not going to consider the normal force for this particular beam. Looking at this lever, exactly what we did for the cube, we took the sum of forces equals 0, and the sum of moments equals 0. The sum of forces equals 0, you get partial V by partial x1 is equal to Q, because basically V will cancel V, then you're going to have partial V by partial x1 acting downwards, Q multiplied by dx1 acting upwards, so dx1 will cancel dx1, and you're going to end up with the rate of change of the shear is due to the loading applied to the beam. If there's no loading applied to the beam, then the shear will be constant. And if you take the moment around this point, you'll find that the rate of change of the moment is equal to the shear. Now, because we have replaced the whole thing with only, we're not interested in x2 and x3, or things do not vary with x2 and x3. The only independent variable is x1. Because the only independent variable is x1, we're going to replace partial d by partial x1 with dv by dx1. So this, or these are the equilibrium equations. That correspond to sigma j equal to sigma ji, and divergence sigma plus rho b equals 0. Those two equations, or the equilibrium equation, sum of forces equals 0, and the stress is equal to its transpose, are equivalent to those two equations, just the same principles, but after we did some integration and certain assumptions, we reached to those equations that apply to a beam. What allows me to call it a beam is how it deforms. I assume the beam deforms such that if, before deformation, the beam has this shape, and I'm interested in tracking this point. This point has coordinates x2 and x1. The assumption is that if this is the plane that's perpendicular to the neutral axis, I'm going to assume that the neutral axis has moved y, which is a function of x1. It's a smooth function that has moved, that describes the movement of the neutral axis of the beam. Now I'm going to track this point. This is the point that I'm interested in, which is this one. This is the distance, because this stayed perpendicular. Then the location of the that point with respect to the neutral axis. The vertical is x2 cosine theta, and the horizontal is x2 sine theta. And so the location of the beam of that point after deformation is equal to the original x1 minus x2 sine theta, and the vertical position is equal to y plus the vertical movement, which is x2 cosine theta. And we assume x3 has not changed. Now, because we assume that this is small deformations, can assume that cosine theta is almost equal to 1. Theta, which is this angle, because of small deformation, we can say that it's equal to the rate of change of y with respect to x1. And theta is equal to tan theta is equal to sine theta, because theta is very small. So we have the new position. I can now calculate the strains. This is the deformation assumption. First, I have to calculate the displacement. U is the U1, U2, U3, the vector of displacements. U1 is equal to x1 minus capital X1, so negative x2 sine theta, or negative x2 theta, because theta is equal to sine theta, or negative x2 dy by dx. And just to clarify here, I've made everything function of one function. That function is y. If I know y, I know the new position, and I know theta because it's the rate of change of y, and I know where the beam has been. So everything is now a function of this unknown y. If I know y, I know everything about the deformation of the beam. The horizontal displacement is equal to x2. Sorry, the vertical displacement is x2 cosine theta plus y minus x2, which, because cosine theta is almost equal to 1, this will cancel this. I'm going to be left with y. And the vertical displacement is 0. Negative x2 dy by dx, y and 0. The strain, because we're using small deformation, I can utilize the small strain, which is equal to half the gradient of u plus the gradient of u transpose. Well, let's calculate the gradient of u first. Partial u1 by partial x1. Negative x2 dy by dx, I'm going to use d2y by dx1 squared. This partial u1 by partial x1. Partial u1 by partial x2 will be equal to negative dy by dx1. 0. Partial u2 by partial x1 is dy by dx1. Partial u2 by partial x2 is 0. Y is only function of x1. Y is only function of x1. It's not function of x2. It's not function of the point, the vertical point, the vertical coordinate of the beam. And the rest will be zeros. Which, when you calculate this and its transpose, you get negative x2 d2y by dx1 squared, and everything else is zeros. So what does this mean? It means that our assumption, our deformation assumption, implies that the only non-zero strain is epsilon 1. And in this case, epsilon 1 is equal to negative x2 d2y by dx1 squared. Okay, I'm going to use the constitutive law and usually ignore Poisson's effect. Ignoring Poisson's ratio, I can say that sigma on 1 is equal to E epsilon 1. So negative E x2 d theta by dx1, where theta is equal to dy by dx1, and so you end up with that the stress is equal to negative ex2 multiplied by d2y by dx1 squared, and that's where you see that the stress is linear on the cross section. The distribution of the stress is linear on the cross section because sigma 1 is only function is equal to E multiplied by a number that's constant on the cross section and multiplied by x2, which means you end up with a sigma 1 that looks like this. This is the cross section of the beam. You end up with a linear distribution of the stress. So all these assumptions lead to a linear distribution of the stress. And when you integrate, you reach the famous formula that the moment is equal to EI multiplied by d2y by dx1 squared. And we know what sigma 1 is, negative ex2 d2y by dx1 squared. So you can find the value of sigma 1 by knowing the bending moment at this point. So this is the relationship between sigma 1 and the moment x2 and I. And similarly, using integration, you can show that the sigma 1, 2, or the shear on the cross section is equal to negative V multiplied by Q, which you divided by I divided by B, where I is the moment of inertia of the cross section and B is the thickness of the point under consideration. So if I would like to create sigma 1, 2 at this point, and this is B, and I is equal to moment of inertia of B at this point. Now there's a little bit of inconsistency in the theory. Now do you notice where that inconsistency is? So I have here sigma 1, 2. What happens when we think about the constitutive law? What happens when I have sigma 1, 2? There has to be shear strain. But what happens when in the small strain? There's no shear strain. So for these beams, we're ignoring the shear strain, or we're assuming it's very small, that it's negligible, or we're assuming that the shear modulus is infinite. All these things are corresponding. But for this, so all the beams that you're actually analyzing, you're saying there is shear stress, but there's not associated shear strain. So why there's no shear strain? Of course, in this point system, it's all because of this assumption of plane sections remaining plane and perpendicular. Because of this assumption, when I consider this coordinate system E1 and E2, there's no shear strain in this coordinate system because these always stay perpendicular. Yet there is shear stress, and the shear stress is calculated using this formula. Sigma 1, 2 is equal to negative VQ divided by IB. So when you replace all this into your equations, into the equilibrium equations, you reach to the equilibrium equation that needs to be solved, which is this. EI d4y by dx1 power 4 is equal to Q. So this is a fourth order ordinary differential equation. I need 4 boundary conditions to be able to solve it. The boundary conditions could be given in terms of y, could be given in terms of theta, which is dy by dx. or could be given in terms of the second derivative, or could be given in terms of the second derivative of y with respect to x. And if you multiply this by ei, then that means I'm giving you the boundary conditions in terms of the moment, or could be given in terms of ei d3y by dx1 squared, dx1 cubed, which is the boundary condition in terms of the shear. So you can apply any of those three boundary conditions, and any of those four possible boundary conditions. I need 4 to be able to analyze the beam. And usually, at any point, the boundary conditions are given in terms of y or shear at any point, theta or moment. Because practically speaking, you can either know the moment that's applied at a point or the rotation or I can constrain the rotation. If I constrain the rotation, I don't know practically what the moment is. So from a practical point of view, I either know theta, which is the boundary condition for the rotation, or the moment, which is the applied moment on the beam. Or I either know y, which is the deformation of the beam, or the shear that's applied at that point. It's not possible to know both. If I know that this is 50, I probably don't know what delta is. If I know that this is 20, I don't know what theta is. But if I know what delta is, I don't know what the shear is. And if I know that theta is 0, I don't know what the moment is. This is just from a practical point of view. But from a mathematical point of view, as long as you give me 4 boundary conditions, I can solve this differential equation. Is that clear? And so, in order to solve this differential equation, you have ei d4y by dx1 bar 4 is equal to q. You can integrate, and you're going to get that y is equal to the integration of q dx, whatever that function q is. If q is constant, so this is integrated 4 times. Plus 4 constants, c1 multiplied by function. No, here will be, so d3y will be c1, c1. So this will be c1 x1 cubed over 6 plus c2 x1 squared over 2 plus c2x plus c3. Okay, so who's taking the finite element analysis course? So you guys understand when I say the degrees of freedom of a system, correct? Hope so. So how many degrees of freedom do I have in the system? 4. I have 4 degrees of freedom. C1, C2, C3, and C4. 4 degrees of freedom. So the beam, the behavior of the beam is known, totally known, by 4 degrees of freedom. Now, in general, those 4 degrees of freedom could be C1, C2, C3, and C4. But I could replace C1, C2, and C3, and C4 with 4 physical degrees of freedom, and those physical degrees of freedom are the displacement at each end and the rotation at each end. And that's when you jump into, and that's how you use the stiffness method. In stiffness method, C1, C2, C3, and C4 are replaced with Y1, Y2, theta 1, and theta 2, and become your degrees of freedom of the beam. The degrees of freedom of the beam would be, I will know everything how this beam deforms, knowing what Y1 is, theta 1 is, Y2 is, and theta 2 is. Knowing those 4 degrees of freedom, I know everything inside that beam. And that's why you can replace the beam, or you can conduct the stiffness analysis of the beam by just looking at the end nodes of the beam. So there's another beam model that I'm going to introduce now, but I'm not going to ask you about it in any exam. Just for just because you might need it at some point. It's called the Timoshenko beam. Timoshenko beam is exactly the same or similar to the other Bernoulli beam, but allows shear deformation. It's applicable more to beams that are less slender. So if I have a very slender beam, then really the assumption of plane sections remain plane and perpendicular. So other Bernoulli plane sections remain plane and perpendicular applies to any slender beam. Once the beam becomes a little bit deeper, I can still assume that plane sections remain plane, but I can also assume that when it deforms, the beam can deform in this manner. Where plane sections remain plane, so they still remain plane, but they're now no longer perpendicular. And that allows for shear deformations. They're applicable for deeper beams, but if your beam is that deep, finite element analysis would be better, simply because finite element analysis would not put that restrictive assumption of plane sections remain plane. In a finite element analysis, maybe each element would have a plane, like the side stays plane, but the next one, they don't necessarily need to be on the same plane after deformation. So the normal force, shearing force, and bending moment is the same. This is just the integration of the stresses on the beam. The equilibrium equation is the same. EI, dV by dx is equal to Q, and the moment, dm by dx is equal to the shear. So these are the equilibrium equations. They do not change. What changes is the deformation assumption. In the deformation assumption, I assume that I have the cross section has rotated with an angle of psi. And psi is the sum of two components. A shear component and a component of so first I assume that the planes rotate but stay perpendicular, and then they shear. So if the plane stays perpendicular to the neutral axis, then you get this angle. Maybe so this is the deformation of the neutral axis. Then this is theta, which is almost equal to dy by dx because of the small deformation, assuming this is 90. But beyond this, we also assume that cross-section has deformed a little bit more, which is gamma, or the shear angle. And so the total cross-section deformation is equal to theta plus gamma. And so replacing theta in the previous derivation with theta plus gamma here, which is psi, and saying that sine psi, because psi is very small, is equal to psi, is equal to sine theta plus gamma. And theta is dy by dx1 plus that gamma. And cosine psi is equal to cosine theta plus gamma is almost equal to 1. And again, using what we've done before, u1, u2, u3 are equal to negative psi x2, y2 is y, y3 is 0, and epsilon, the strain, which is equal to half the gradient of u plus the gradient of u transpose. Now we end up with negative x2 deep c by dx1 and negative gamma. So unlike the other Bernoulli beam, I'm able to, when I now have a shear sigma on 2, I have a corresponding shear strain. Similar to what we did for the other Bernoulli beam, sigma on 1 is equal to negative E epsilon on 1. Epsilon on 1 is equal to negative x2 deep c by dx1. So sigma on 1 is equal to negative ex2 dc by dx1. When I integrate sigma on 1 to find the moment acting on the cross section, I get this famous equation. M3 is equal to pi deep c by dx1, where c is the cross section rotation. Now, the shear is assumed to be equal to negative gamma on the whole cross section. The shear stress kind of an average shear stress acting on the whole cross section is equal to negative K multiplied, which is, this is, K is a cross section. Or is a factor. Bending on the cross section. G is the shear modulus. And gamma is this shear angle. And when you integrate this quantity, you end up with the shear force is equal to kGa multiplied by gamma. So the final equations that are solved, this is the equilibrium equation, and the boundary conditions are usually given in C, which is the cross-section rotation, or the moment, which is EI deep C by dx1, or the shear, which is equal to EI into C by dx1 squared. And to find the deflection y, we have to solve another differential equation, which is dy by dx1 is equal to C minus EI over K. So this is gamma, C minus gamma, because we said that C is equal to theta plus gamma. So theta, which is dy by dx, is equal to C minus gamma, and gamma is replaced by EI. So this is C minus gamma. And so these two differential equations are solved to find cross-section rotation and the deflection of the beam y. Now, as I said, I just introduced this beam because you might use it in one of the courses, or you might in the future try to use it in any finite element analysis. So you need to understand what the basic assumptions behind this beam are. Just for illustration purposes, before you guys look at this, which one is more flexible, do you think? Under the same loading, which one would deform more? Fatima, do you have an idea? Yes. So who didn't hear Fatima? What do you guys think? Which one? The second one. Yes, the second one is more flexible. So when you look at the deformation under the same load, depending of course on the length of the beam, and so you have an example in your book, you can copy the code and put it in Mathematica and play with the EI and play with the, I think, KAG divided by EI, and see how the beams deform with respect to each other. And the two-chamber beam is more flexible. And that's why it's sometimes called shear flexible beam. So in small deformations, I can, when I look at beams, I can decouple the normal force and the bending moment by decoupling, I mean, we usually consider the normal force does not affect the moment and the moment does not affect the normal force. Because of this, we separated the behavior of the beam under bending and the behavior of the beam under normal force. So I can now look at a beam, and we've done this in the FEA throughout, a beam under the distributed normal force P, which is a function of x, and I can extract a sliver of the beam and look here at sigma on 1. Here sigma on 1 plus a little bit more. And if this is the area, and if this is the area plus however the area changes with respect to x1 dx1, and if this is the distributed load P, then you end up with the equation that says that the rate of change of sigma on 1 multiplied by the area divided by dx1 is equal to negative P, where this is the normal force. The deformation assumption, plane sections remain plane and perpendicular. So any plane, I assume it just moved as a whole, horizontally, at distance u1 of x, because depending on which, so I assume that the beam has moved horizontally, and so because u, the only thing I have is u1 and 0, 0, then the small strain will be equal to partial u1 by partial x1, and everything else is zeros. Because everything else is zeros, then I can say that sigma on 1 is equal to E epsilon on 1, which is equal to E du1 by dx1. And so the final equation is dn by dx1 is equal to negative P, and n is equal to sigma on 1 multiplied by the area, which is equal to EA du1 by dx1. And so you end up with the equation that says dEA du1 and you need, this is a second order differential equation, you need two boundary conditions, and the boundary conditions are usually the load or the displacement, the load, so the normal force or the displacement, the normal force or the displacement, N1 U1, N2 U2, either or. And if you do the integration, you see that this, the behavior of the beam, is function of two constants. Those two constants, because this is a second order, so when you do the integration, there's going to be constant 1 and constant 2. So the system is known, the system is fully described if you know the constant 1 and constant 2, because u will be equal to the integral of a function twice plus a constant 1 multiplied by a function plus another constant 2 multiplied by plus another constant 2. So the system is fully described by two constants. So the system has 2 degrees of freedom. And so for a beam under normal loads, we also add the degree of freedom u1 and the degree of freedom u2. So we can replace the constant 1 and constant 2 with the displacement u1 and u2. And knowing u1 and u2, I know everything about how this beam behaves under normal force. And that's the 2 degrees of freedom that's also added in the stiffness method. Now I know you guys are studying the stiffness method, correct? In the 660. You end up with, for for the stiffness method, if you can easily jump from here to the stiffness method by saying that I have a beam that has 6 degrees of freedom, U1, V1, theta 1, U2, V2, theta 2, and you put them here, 6 degrees of freedom. 6 degrees of freedom have 6 corresponding external forces acting on that object, acting on the beam, and inside here you will find that the horizontal displacements and the rotations and moments are decoupled. By decoupled, you'll find a lot of zeros whenever U1 and V1, any row that corresponds to U1 and V1, you're going to find zeros because the horizontal and the vertical displacement are decoupled. All right, so I'll give you 5 minutes. Oh, maybe here. There's
Yes.
Can I get those? Thank you. Where was she? They're really close to this.
Do you have one?
They are. You didn't find it?
Yeah, I don't think he has some in the back. One of the assignments, maybe we can just get him to post which ones we need.
Yeah,
Because there's probably like 3 different ones.
Oh, yeah. Look at this one. I think they are. The solutions are posted. Have you guys checked?
yeah, they're.
So compare yours to the solution. If you have any questions, let me know. So why are you upset?
Well, I want to look at the question again, I guess. Like, I just didn't answer. We didn't answer. Or like didn't fully answer it. So he's like, where's the rest of the answer?
我交之前我让我检查好吗？然后
赶紧抓紧时间找个对象吧。
气死，因为有的时候自己检查不出来的，自己是吧？我让他帮我检查，那你给我检查了。
Let's grab it.
跟那个新书就说不一样，你们说这个
Under 50. I worried about.
现在没题吗？
第六个。
不好意思，